Hello and welcome to another video. In this video we're going to go over all the problems of the Biweekly Contest 128. And this is actually probably the easiest one I've done so far, or close to it. So let's go through it. So for the easy problem, it's really easy. All you have to do is compare, they basically tell you the score is defined as the sum of the absolute difference between the ASCII values of adjacent characters. So for every character, you just compare it to the one after. You just do a minus, like this. So you just say like, okay, let me get the ASCII value of this character, subtract this, get an absolute value, and so on and so on and so on. So it's like a 5-second problem, and they kind of show you what you do here. And you basically just get all the ASCII values of every character, compare it to every character after it, and then you're done. And then, yeah, as you can see, it's literally like one line of code. So not much to say there. So let's go to the next one, and here we have a picture of it. So the next one is you're given a 2D integer array points, and you're also given an integer w, and your task is to cover all the points with rectangles. So the basic idea here is you have a bunch of points, and you can make rectangles that are up to w wide. So here, like w is 1, so your rectangle can be up to w wide, and you have to cover all of your points with rectangles, and covering includes if the point is like on the perimeter of the rectangle. That's fine. As you can see in most of these, this is the case. And you basically are asked, like, what's the minimum number of rectangles you need? So in this case, 2 rectangles will cover all the points of width 1. In the second example, you can have width 2, so 2 or 3 rectangles will cover that. And then the third example, you can have width 0, so it's just one on each one, so it'd be 2. So the basic thing you have to understand here that makes it really easy as well is the height of the rectangles can be whatever you want. So the y value of these points doesn't matter. Like if this point is here or at like 1,000,000, you'll still have the same rectangle, it'll just be taller. And so that's kind of the idea. So the only thing you really care about is the x values of the points, because you can just make your rectangles infinite height. And so basically all you have to do is you have to sort the points. So you sort the points, they look something like this. And then you just go through it. So like, let's say we sort these points in like this order. Then we basically just say like, okay, our first point will be the start of a rectangle. So let's say we start here. And then we check, is our next point a distance w or less away from our start? So this can be part of the first rectangle. Then is this point the distance w or less from our start? Yes, it is, right? Because our start is at 0. So this is also distance w away. So this is all one rectangle. Then we get to this point, and this point is too far away from our start. So now we basically say, okay, that last start, that's a rectangle. We add 1 to the result, and now this is our new start. And then for this point, we just check, is it w away from the start? Yes, it is. Is this w away from the start? Yes, it is. And now this point is too far away from our old start, right? So our starts of rectangles were here and here and here. And because you have to start 3 rectangles, you just have your answer is 3. And so we can look at the other examples as well with that. So here, let's say our first point, like I said, the y values don't matter, but let's say our first point is here. So the start will be here. Then our next point, let's say, is here, and we check, is that w away from the start? Yes, it is, because it's the same exact x value. This is the same exact x value, and now this point is w away from the start as well. So this can all be in one rectangle, and this was our starting point. Then we come over here, and this is too far away, so now we make this our new starting point, and we add 1 to our rectangles. And then this is close enough, so this can be all part of the same rectangle. So that's the basic idea, is you just sort your x values. You can literally cross out your y values. They don't matter. Your rectangles can be infinite height. And in the same one here, so your w is 0, so our first point will be our start. And then our second point is, in order for it to be w away, it has to be the same exact x value. It's not, so we have to make a new start value here. And so because we made 2 start values, we have 2 rectangles. And that's basically it. So if we actually look at the code, really easy. So you just sort your points by x value. And then I just made my start negative infinity. And then you just go through all your x values and you say, if my current x value is less than w away from my start, then it's all part of the same rectangle. Otherwise, I make a new rectangle and then I make a start right where I'm at and I return. So pretty straightforward. So let's take a look at the next one. So in the next one, I don't even need to draw a picture. So basically here you just have a graph and you have edges. So this is just like a typical graph, unweighted graph with edges and a length of the edge. And so they tell you that you have to start at node 0 and you have to get to every other node. And so to start at node 0 and get to every other node, you can just do like a normal traversal, and they tell you what's the minimum time to reach node I from node 0, and if it's unreachable, return -1. And the only caveat here is you have this disappear array, meaning if you reach a node at this time or more, the node won't be there. So it's pretty straightforward. Like, it's just a basic graph traversal, and all you have to do is just build up an adjacency list, and then you start at node 0, and then you just try to traverse to every node. So it's literally just a straightforward Dijkstra's. And the only difference is when you get to a node, like in a normal Dijkstra's, whenever you get to a node, that's the minimum distance. But now when you get to a node, you check, like, let's say I get to this node at some time, you check, is that node disappeared or not? And if that node is disappeared, then I just like continue, and then I return -1 for the node. And if it's not disappeared, then you just do a normal Dijkstra's where you look at its children that haven't been visited yet, and you put those in a heap. And there's a slight optimization that I'll show you in the code, but that's basically it. So it's literally just Dijkstra's from the starting node, and then whenever you get to a node, you just check, has it been disappeared yet? If it hasn't, then continue on doing normal stuff. If it's disappeared, just completely ignore it and go on to the next thing, and then just leave this. So what you can do is you can set all your outputs to -1, and then whenever you get to a node that is actually not disappeared, you would just update its value. But it's literally just cookie cutter Dijkstra's with like 2 more lines of code. So I'm assuming if you do leak code contest, you should know what Dijkstra's is and like how to do it. So let's go through that. So you make a basic graph, and then because I have a node and then also a distance, I just made every node will have its own dictionary. And so this depends on the language, but essentially you build up an adjacency list, whatever format you want, whatever language you want. Then you just make your result all -1s. You make your heap your starting node. You make a visited set. Then you pop your node and you check, have I been here before? Just like normal Dijkstra's. And then you get the oh yeah, so I forgot. So the reason I'm not checking if it disappeared here is because what I do is, if you look at the disappeared results, they can be disappeared or at 1 or more. So the first node is guaranteed to not be disappeared. So what I do is I just make the result at the time. And the reason I don't have to check for disappeared is because I actually do it here. So whenever I'm at a node, like let's say I'm at node 0, and I check for the children. So I'll check like, okay, I'm at node 0, and then I'm going to add node 1. The time will be 0 plus 2. I check, will that node be disappeared by the time I visit it? So you can just check for the disappeared before you even add it to the heap. That's why you don't need to check when you pop it. So it's a basic just the Dijkstra's, and then this is literally like 1 more line of code here. And then everything else is just standard Dijkstra's. So basically you just keep track of your like total time to get here, and then for your current node that you popped, you check, are the children not visited, and if I do visit the child, will it have been disappeared? If it would just disappear, then I just completely ignore that node. If not, then I actually put it into my heap. And then the rest of it is like, yeah, like I said, literally 2 lines of code difference from Dijkstra's. So, okay. So that's that one. Yeah, and I think I actually got pretty good runtimes for these. So let me just check. Yeah, I mean, maybe there's like not a lot of solutions, but I don't really know how you would make it better. Like I think this is like as optimal as it gets. So let's take a look at the last one, and this is like the only tricky one. So let's get rid of these. And yeah, the first 3 are pretty straightforward, like really easy. The third problem is basically just Dijkstra's with like 2 more lines of code. So let's take a look at this one. And this is like the tricky one. So here, you're given an array of numbers, and you want to return how many subarrays there are that the first and last value are the biggest value in the array. Okay, there we go. And so if we take a look at this first example, so an array can be length 1. So you would always have like the length of the array. So you have 5, but you also have this one here. And then in the second example, so once again, all length 1 arrays, but then you also have this length 2 array, this length 2 array, and then this whole thing. And then in the last one, there's only 1. And it's 10 to the 5th, so you're going to want like an n log n or something solution. So first of all, let's just go over really quickly how to, like, let's say we didn't have this constraint that the first and last element are equal to the largest element in the array. Like, let's just say we have some array like this. And let's just say we have some numbers. So let's say we have like 1, 2, 1, 2, 3, 4, or 3, 3, 4, 4, 3, 1. So let's say we're asked like give us the number of subarrays where the first and last element are equal. So that one should be like a pretty straightforward problem. There's a bunch of them like that. Basically, for every single index, we can just keep track of like how many subarrays can we make with this being the last index, right? And assuming these could be length 1, obviously, you can make one at like every time, right? Like this could be a subarray, just this one number. This could be a subarray. This could be a subarray, and so on. So all we really need to do is keep track, like know how many ones there are before this one. So basically, we would have a dictionary. So let's have a result value. And all we need is a dictionary of how many ones have we seen before. And then for every one that we've seen before, we can just connect that previous one to this one to make an array. So in this example, there are no ones that we've seen before, so we're just going to add only one, right? Because we can make the subarray of just this one thing. And then we're going to say we've seen one time now. Then we go to the next thing. So we haven't seen a 2. Let's actually move this over here. Okay, so we haven't seen a 2, so we can't connect this to any other 2s, but we can make an array of length 1. So this will be 2, and now we've seen a 2 once. Now for this one, we've seen a 1 already. So that means for every one we've seen, we can make a subarray with that 1 and this one, right? Like this would be a subarray. So that's 1, and also we include the array of length 1, so this will be 4. And now we've seen 2 ones. So then we go to the 2, and same thing. For every 2 we've seen before, which we've seen 1 of, we can connect this 2 to the previous one. So because we've only seen 1, we can make this. Plus the array of length 1, so 6 total. And now we've seen 2 twice. And so that's basically the idea here. So we can keep going. So 3, we haven't seen any, so this should just be the 1. Then we've seen 3 once. And then here we've seen it already, so we can connect it to that one plus the 1 itself. So there's 2 there. So this will be 9. And then there's 2 3s here that we've seen. Then for a 4, same thing. First time we haven't seen anything, so 10. And then the second time, so it would be like this after the first one. Then after the second one, there's 2 here, right? There's this and this, so that's 12. Okay, so now we get to the ones we've seen before. So we've seen 3 twice, so we can make 2 subarrays connecting this 3 to previous 3s, right? This or this, plus the subarray of length 1, so this is 15. And now we've seen 3 times. And for the 4, same thing. We're going to connect the 4 to the previous 2 4s and the single one, so it's 3 more. So that's how you do it with no like constraint of the left and right have to be the maximum. But now, so that kind of gives you the idea of how to count subarrays. And I think I've done a bunch of like the problem of the days like this. But now the difference is we need our subarrays to all be like we can't have something like this, right? We can't have something like this because the biggest element in here isn't a 4. So we need the biggest element to be on the left and the right. And the way to do that is we can kind of have the same idea. We can keep track of how many we've seen. But let's say we have like a 3, like let's say we start here. Or let's actually say we start here. So we've seen a 1. But once we get to a 2, we can no longer reuse our 1 because the biggest element in arrays with the previous ones wouldn't be a 1, right? So anytime we get to a number bigger than numbers we have stored, those numbers are no good anymore. Like we can't make subarrays with them anymore. And so the basic idea is like, well, if once we get to a number that's bigger than elements we've seen before, those are no good. What does that sound like? That sounds like a stack, right? So we can keep a decreasing stack, and then whenever we get to a bigger element, we can just start popping off all our numbers because those are not going to be able to be reused. And so that's the idea. So basically to add, to make sure that the smallest and biggest element are the same number, you can just have a decreasing stack. And the left bound would be true for that because you have a decreasing stack, right? So in order for the left bound to be true, like our numbers would have to be stored like 4, 2, 1. So the left bound would be true, right? Because because like basically there's not going to be anything bigger to the left, or sorry, it doesn't matter what's bigger to the left. There's not going to be anything bigger to the middle. So let's kind of walk through the stack variation of this and see what we would get here. Okay, so basically what we're going to store now is we're going to store instead of just storing the number and the count. Actually, no, we are just going to store the number and the count, and then we're gonna write like how many subarrays we can build, right? So yeah, that is fine actually. So let's do that. So we get to a 1, and our stack is empty, so we can just put the 1 on the stack. So we'll say, okay, we're going to have a 1, and we can build 1 subarray. So this is what we're going to store. We're going to have the number and the number of subarrays we can build. So we'll store this in an array. I'm just going to draw it like this, but we'll store it like this. And anytime we put something on the stack, we can just update our result. So we have 1. Now we get to a 2. So we know we can't connect 1s past this 2 to previous 1s because the 2 will just be too big. So while we have a stack, and while the last item is smaller than this, we can just pulp. Because none of these things before the 2 will be connected. Like there's a barrier here, right? Anything that's smaller than the 2 won't be able to be connected. But if this was like a 3, then it would still be fine because this would be good, right? So that's why you have the decreasing stack. So like storing 3, 2 would be fine, but you can't store 1, 2. So we're going to pop this off. And then we're going to add a 2 with a count of 1 because that's how many subarrays we can build. So now our result will be 2. Okay. And then we're going to get to this 1. And so this is fine. Like we can add this on because like let's say this was a 1. This would be a viable subarray and so on. So decreasing stack is fine. So what we're going to do is we're going to add a 1 with a count of 1 to our stack. So our stack will be like this. And then we are going to increment our result. Now we get to a 2. So now that we get to a 2, this 1 can no longer be used with any 1 to the right of it, right? Because the biggest number will be 2 or bigger. So we can pop this off. This is completely useless. And now we have kind of 2 cases. We either add a new number or we just increment our old number. And we're guaranteed to either have a decreasing stack or an equal number here. So because we have an equal number, we can just increment this. And the number of subarrays we can build using this number is actually 2, right? It's going to be this one and this one. So we can add 2 here. Then we get to a 3. And like I said, once you get to a 3, nothing less than a 3 here can be used for something for the same number here, right? Like if we have 2s here, we can't connect it with 2s here because we have a 3. So the biggest number will be 3. So basically we can pop this off. Then we can add a 3 with a count of 1. And now our result will be 6. Then we come over here and we have another 3. So we can increment this to 2. And now we will add 2. So that's kind of the idea. You just keep track of how many of the number you have. And then every time you increment it, that's how many more subarrays you get. So here we have 8. Then we get to a 4. And once again, when we get to a 4, all these 3s can't be used anymore for things to the right because the 4 will be the biggest element. So we pop off this. We add the 4 with a count 1. And now our result is 9. And then we add another 1. So this will be count 2. And now our result will be 11. And then 3 is viable, right? We can have decreasing numbers because, like, let's say we had a 3 here and then a 3 here. That's an array, and also the 3 by itself is an array. And these 4s are still viable because, like, what if we had a 4 here? These are all still viable, right? So that's where the decreasing stack works. So you would add a 3 here. So let's do that. Let's get rid of this. So our stack is now 3 with a count of 1. And so that's another 1. And then we have a 1, which is also viable. Decreasing is fine. So 1 with a count of 1. So our stack is 4, 3, 1. And now our count is 13. And then because we incremented our result every time we put in a new number, now we don't need to like pop off these things from the stack and do anything. We're just done. So we have 13 arrays total. So we can actually walk through this example as well, just to show how to get the 6, and then we can be done. So I'm not gonna like show all these, but I'll show the stack. So in the beginning, we'll have 1 with a count of 1, and that will give us a result of 1. Then we get to a 4, which is bigger than 1, so we pop off the 1. Then we put on the 4 with a count of 1, so that's another 1. So now our result will be 2. Then we get to a 3, which is viable, so 3 with a count of 1. So now our result will be 3. Then we increment our 3 to 2. So now we have 2 more we can build, so 5. And then finally we have 2, which is also viable, so decreasing stack. And that's just 1, so we have 6. That's kind of how you do it. So the code is pretty easy, but it is kind of hard to figure this out. And what I like, the intuition you probably are going to get is like, you want to figure out where the next greater element is for each number. But if you just do that, that's going to be too slow because you can't just like compare it. But what you could do, like an intuition you might come up with is like, where's the next greater element for each number? And then how many numbers of this number are in that thing. So what you could do is you could store like every number and all the locations where it is in an increasing order, because you can just go through this array. And then you could say like, okay, for this number, let's say, what's the next greater element on the left side? And then let's say that is at some index. Or for example, let's say for this, let's say for this is like some index, right? We could say like, what's the next greater element on the left side? It's going to be over here. And then we could just figure out like with a binary search, how many 2s are before that next greater element. So that's a little bit more intuitive. So there's like a binary search stack solution, or like just a binary search dictionary solution as well. It's a little bit more intuitive. The stack one is not so intuitive, but it's like obviously the cleanest one, and it makes a lot of sense once you see it, because you just realize like, okay, whenever I get a number that's bigger, like once you can visualize it like that, like when I have a number, numbers to the left of it that are smaller than that number can't be connected to numbers to the right of it. So I can just take numbers to the left of it and get rid of all those, and so on. And that's why the stack needs to be decreasing. So the code is pretty easy. It's basically you just have a stack result, and then like I said, while we have a stack and the current number is bigger than our last number, we pop. And then if the number we're trying to add is the same number, we just increment that count by 1, and then otherwise we add a new number with a count of 1. And finally, at the end, whenever we add, we increment our result by the count of whatever the last thing is, and we just return it. So this is obviously like as good as it gets for this one. And yeah, so it's going to be all for this contest. Like I said, definitely probably the easiest one I've seen so far. I mean, this problem is definitely not super easy. The first 3 were like just super easy, I think. Like I think I did all those in like less than 20 minutes. But this one definitely does require a bit of work. So, but yeah, if you have any questions, as always, write in the comments, and I'll provide this code in Python. I'll probably provide this code in other languages as well, just because it's pretty simple. But yeah, I'll see you in the next one, and thanks for watching.